I would like to welcome everyone to today's webinar. I am very happy to welcome all of you to this event where we are going to provide you with insights into the role of simulation of oil management for transmission using moving particle simulation. My name is Alina Jubiler from the company EnginSoft, and I will be your host for this event. That being said, I suggest we dive right in and have a look at the agenda before we move on to the introduction of the speakers. Today, we have 3 presentations planned for you by 2 different speakers whom I will introduce to you in a second. This session's focus lies on the 4th presentation that you can see on the agenda right here and should take about 1 hour, just depending on how much time we will spend on the Q&A session in the end. If you would like to contribute any questions to the Q&A session, then please feel free to communicate us your questions in writing through the chat, and we will try to answer as many questions as possible at the end of the presentation. Now, I would like to move on and briefly introduce today's 2 key speakers to you. First, I would like to go ahead and introduce our guest speaker, Mattia Porchetta. He currently works as oil management engineer for Tremec in Belgium and will provide us with industry insights into the role of simulation on how to improve the oil management in transmissions for high-performance applications. Mattia, thank you for joining us here today. Perhaps you'd like to give a small wave so everyone knows who I'm talking to. And I really hope I got your last name slightly right.
Yes, thank you.
Thank you. The other speaker I would like to introduce to you is Simon Habecke, who works as application engineer here at EnginSoft Germany. He has prepared an introductory presentation on Particleworks and its moving particle simulation, as well as an overview of Particleworks applications in powertrain and drivetrain for you. Welcome, Simon. We are glad to have you too. If you want to give a small wave also, so everyone knows who you are.
Hello, everyone.
Thank you. All right, then, I believe that is all the introductory information you need to know before we dive into the technical part of the webinar. I would now like to transfer the moderation rights to Simon Habecke so he can get started on the first presentation. There you go.
Yes, thank you. So I will share my screen, which you should see now. So as Alina said, I will take you through a brief introduction of Particleworks and the underlying methodology, the moving particle simulation, and then also present some recent use cases that have already been presented before, and then hand over to Mattia, who will tell us a little bit about Tremec's application of Particleworks in their development process. So Particleworks is a particle-based CFD tool which uses a numerical method called the moving particle simulation. The moving particle simulation was originally proposed by Professor Koshizuka, who's a professor at the University of Tokyo at the Graduate School of Engineering. He is also a co-founder of Promotech Software, which is the developing company behind Particleworks, and he proposed this method basically as an evolution to the smooth particle hydrodynamics in 1996. So for those of you who are familiar with CFD in principle, you might be familiar with the so-called finite volume method, which is an Eulerian CFD methodology where you basically discretize the fluid volume with a numerical grid on which the liquid movement or the fluid movement is solved and simulated. Instead, with the MPS, so the moving particle simulation, it used a particle-based approach. So that's the definition of a Lagrangian approach, where the liquid is discretized, so the fluid is discretized by a set of dynamic particles. So basically, we can understand our particles as dynamic calculation points which represent our fluid, and these fluid particles, they interact not only with each other, but only, of course, with the other boundary conditions that we can impose on the simulation model. And also the MPS, just as most of the finite volume methods, also approximates the Navier-Stokes equations as the fundamental governing equations in computational fluid dynamics. So Particleworks is a tool that, as said, uses the MPS, since we do not need to extract the fluid volume, but instead can discretize the liquid with our particles. We're talking about a mesh-free method, which is especially suitable to simulate free surface flows and related problems like liquid sloshing or liquid jets. And then, of course, as we see here in this animation, we can also simulate the interaction not only with rigid bodies, but then there would also be other applications where we can potentially extend the model to also introduce sand into the gearbox, for example, which in real life, of course, we want to avoid, or also include flexible bodies into the system. And then what we see here on the right-hand side shows Particleworks' capability to also simulate highly viscous or non-Newtonian fluids such as grease. So the type of applications which we can handle with this sort of methodology or range from oil splashing and lubrication of gearboxes and transmissions, and we will learn later more about that from Mattia. Then in the overall topic of lubrication, of course, we can also have a closer focus on bearing itself. Then with the same methodology, we can also handle certain applications in the field of engine or piston lubrication and also cooling. So this actually covers both conventional internal combustion engines as well as electric engines, which nowadays can also be or are more and more internally cooled by oil jets. Then in a slightly different industry, in the energy sector, we can also perform simulation of hydro turbines, which is particularly efficient for turbines like a Pelton or a Banky turbine, so where we also have free surface flows. And then more focused on the process or chemical industry, we can also simulate highly viscous or non-Newtonian fluids ranging from chocolate, glue, cement, or grease, just to give you some examples. So now we see all these nice animations which show basically some of the visualization options that Particleworks can provide us during the post-processing. So in the next slides, I will give you a very, very brief overview to give you some impressions about how such a simulation is potentially set up. So to give you an idea of the simulation workflow. So the first step actually takes part before the simulation, so with the geometric preparation of the model, which we then import into Particleworks. In principle, we do not need to perform any larger simplifications, but basically we just export each part, like a shaft or a gear, that later in the simulation model we want to set with a separate kinematic motion into a separate file, and then export these parts as separate STL or OBJ files, which are, let's say, the formats that Particleworks can read. So inside of Particleworks, we basically import the non-simplified geometries. Then in the next step, we define the analysis conditions. So that includes, first of all, of course, the material properties. which characterize our fluid. For oil, this would of course be the density, kinematic viscosity, some surface tension parameters. Then we of course also need to define the kinematics, so the motion of our shafts and gears. And then to introduce the oil or the liquid into our simulation model, we can either define, or actually can define both in the same model, define a filling plane, which can introduce an initial fill level into the simulation model, and then also create inflows and outflows, which basically can introduce new fluid, new oil into the simulation, and also take simulation out of oil out of the simulation. And therefore, this also enables us to model forced lubrication systems. Then, of course, since we're talking about a simulation tool, we also need to set some numerical parameters like the time step, which is typically estimated by our rotational speed, and the particle size, which we are using for the simulation, plus some other numerical settings, which we won't cover in this webinar. So after we imported the geometry, defined our kinematic conditions, we perform the post-processing. So during the pre-processing, of course, comes first. So we perform the pre-processing, during which the geometrical model is first automatically translated into the internal calculation model, which is used by the actual simulation. And then also the initial particle placement, for example, during the fill operation, is also performed, so that our gearbox might also already be pre-filled with oil particles. Then during the actual simulation, we of course perform the calculation, which will calculate our liquid movement. We can use one, or depending on the model size, multiple GPUs. We can also leverage CPU clusters, while according to our experience, the use of GPUs is more efficient. The software runs both on Windows and also on Linux. And then now coming to the aforementioned post-processing. This, of course, gives us the insights we are looking for by using the simulations, which can be the visualization of the oil flow. We can export animations, then in principle also evaluate the churning losses, and also, of course, measure flow rates and the oil distribution in different parts of the housing. So the advantage such a meshless simulation approach gives us is the overall reduction of the simulation time, since we do not need to simplify the geometry, we do not need to perform any meshing, and it's very robust and easy to implement complex kinematics. So now coming to some applications that have been presented in webinars or at conferences before. I will just give you some key points. And since some of the case studies have been presented at the International CAE Conference, I also wanted to give you a brief hands up about the International CAE Conference, which will take place actually next week in Vicenza, Italy. And while it was held as a pure online event last year, this year it will actually be held as a private event. So you can still register under this link to take part into the conference also via web. So the first application I wanted to give you a brief peek into was presented by Ducati course at the CAE conference last year. And in this case study, Ducati presented their application to evaluate and then also optimize different nozzle configurations with the aim to maximize the HTC distribution on the undercrown of a motorcycle piston. And if you scan the QR code on the bottom right side, you will come to a link where you can view, I think, a trailer or a review of the actual presentation. Then a similar application from a, let's say, software perspective, in terms what was simulated, was also presented at the last CAE conference in collaboration with Ricardo, but this time the aim was to simulate the internal oil cooling of an electric motor, and then with the target to compare the winding temperatures at different locations, also with experimental values. And in that simulation workflow, Particleworks was used to simulate the oil distribution and HTC distribution on the windings due to the oil jets, which are sprayed from the rotor shaft, to finally then calculate the resulting temperatures in the windings with the help of an FE tool. And in the result of this case study, we are also provided with some absolute values regarding the difference between experimental values and measurements, which were below the requirement of 5 degrees Celsius. So this gave some confidence and validation into the use of Particleworks for such applications. So now I will come to the last case study, which was presented by Comer Industries, I think, at the CAE conference 2019, or actually 2018, where the objective was to simulate the oil distribution in a coupling gearbox between an electric motor, between an axle of a wheel loader, and the aim was to compare the oil distribution in different operating conditions, different, like the mounting position and also the operating speed, and finally to assess the bearing lubrication in all these different operating conditions. So in here, they not only did a visual comparison of, let's say, the oil flow patterns, but also evaluated the, let's say, the qualitative lubrication of the different bearing positions with the help of a qualitative scale. And in there, we found, or Comer actually found, that there was a very good correlation between experiments and tests for this type of gearbox. So just by the coloring, we can see that there was a very good correlation between experiments and tests. And my personal highlight is this sort of flooding of this bearing, which could be identified both in the simulations and the experiments. So this would be my part of today's webinar for the moment, and I'll be glad to hand over to Mattia to learn something new about the use of Particleworks in the transmission or in the transmission development.
So hello everyone, and good afternoon. Thank you for joining the webinar. As Alina presented me, I'm a member of the development team at Tremec, Belgium, and actually during the last 3 years, I've been mainly responsible for the oil management in our products. Today, I'm going to present a case study that's representative of, I will say, one of the very first application of the MPS method to our products. Hope you can see my presentation. Before going into the technical details, I'd like to quickly introduce our company. So with Tremec, actually Tremec is a drivetrain and transmission solution company. It's part of the QO group. We have 3 facilities with our headquarters in Querétaro, Mexico. Then we have 1 facility in the States, Wixom. And finally, we have our facility here in Belgium at Zidegem. Tremec is mainly known for its manual and dual transmission more recently for high power and high torque applications. For example, we have the TR9070, that's our inline DCT, and the TR9080, that's our transaxle transmission. The first can be found in the Ford Mustang, the Shelby GT Shelby 500, and then the transaxle transmission can be found in both the new Maserati MC20 and the new Corvette C8. With the market shifting towards electrification, we're also evolving our portfolio. We have some hybrid ready transmission, still based on our TR9070 and TR9080. We are currently developing a new HDCT transmission that will integrate an electric motor, and we are also working on some e-axles. For example, Hydra, that's hybrid driven axle. For the test case of today, I will refer to the TR9070. So as I said before, it's our inline DCT transmission. It's 7-speed. It can transfer up to 900 Newton meters with a maximum input speed of 9,000 RPMs. And it can shift in a very, very short times of only 80 milliseconds. So why is oil management important for our products and in particular for our transmissions? Well, first of all, because of lubrication. In general, we want to avoid the metal-to-metal contact between mating surfaces, as this can lead to excessive wear or even damage and potential failure of the part. Not only that, then also the lubricant can act as a coolant, so it's needed to dissipate the heat generated. There can be different strategies for lubrication. I will not go in detail, but some of these are, for example, splash lubrication or forced lubrication. So it's important to have a proper lubrication in the transmission, and it's also important to do this efficiently. Well, I think that all of us know then that it's very important, for example, nowadays for car manufacturers to keep low the fuel consumption. But not only this, inefficiency will translate into heat generations. This can potentially lead to high temperature and overheating and hotspot issue. So being efficient means that we can say easily, it's going to be easier to design a proper cooling circuit and cooling system. And downsizing also of some of the components like the heat exchanger. One of the last points is then related to actuations and mainly the feeding of the hydraulic circuits. It can be challenging for high performance application like sports car because they are capable of very high G level in both lateral and longitudinal directions. So the oil will tend to move a lot within the transmission. And if this happens in the sampan, where usually the pickup of the pump is located, this can lead to oil starvation, causing a suction issue that can potentially lead to disengagement of the clutches, and then not being able to transfer the torque and power anymore. This is of course not acceptable for such a product like a sports car, and it will certainly affect the drivability of all of these items are strictly related one to the other, and one change in one of these can affect the other. One of the last points that we focus on is the behavior and the proper functioning of the breather. So usually we have a air venting system that allows the hot air to expand through it, and the cold air to get in. This is needed to avoid overpressure and overheating inside of the transmission. Of course, you don't want any oil to get out of it because it can be quite risky, and even with a potential risk of fire in case this oil gets in contact with hot parts outside of the transmission, like the engine and the exhausts. So how do we monitor all of these parameters? Well, first of all, we started with CFD. We extensively use the moving particles method. This is during last year, it resulted to be quite effective, and it's a powerful tool. It gives you a lot of flexibility. It's very easy to change the geometry and perform thoughtful experiments like playing with the input conditions and the boundary conditions. And we mainly use this to drive the design from the very early phases of our project. Then when we come up with a prototype, the first thing that we do, we perform some tests. We initially do this on benches. For example, in the picture below, we have a very capable bench. It's a dynamic tilt test bench that we use to correlate with track data. This bench allows you, for example, to tilt the transmission along the pitch and roll axis. Of course, these kind of tests are still quite flexible in the sense that it's easily to reach the transmission and modify it. Then it's also quite easy to instrument the transmission. For example, you could also use some transparent features and transparent covers to see through the transmission to catch the oil motion. Although the price from the CFD to this kind of test increases, and also they will need some preparation because you will need to provide all the parts and components for the test itself. The final validation, of course, has to happen in the vehicle. This, I will say, is the least flexible kind of test because it's very difficult to access the transmission. It's time consuming and also very, very expensive. So usually you want to perform this kind of test during the last phases of or advanced phases of the program. You don't want to really use this kind of test for the initial development of your products because it's going to be very, very expensive. So what happened with our TR9070? Actually, at that time, we were not using the moving particle simulations method. So we didn't go through the workflow that I just presented. And we ended up in a very late stage of our program with a suction issue. This happened in the vehicle. We were testing at Gingerman track, and in a specific corner with a specific driver, what happened was that after the long straight, when braking into a left corner, we experienced some oil starvation in our sampan, and this led to a system pressure fault with the clutch disengaging and not being able to transfer the torque for a while. At the time, we then spent a lot of time trying to solve this issue, performing some track tests. I'm talking about like 4 to 5 months without succeeding in it. And we decided then to move to some dynamic tilt test at Toyota. Like we can see here at the top left is it's video from the test we performed there, where during one of last test session we were able to test with a transparent feature. When going to this test bench, we still spent a couple of months trying to solve the issue without succeeding. When we finally decided to contact EnginSoft and perform some simulations of this specific maneuver. So here at the top, you can see the comparison between the test results and the CFD results. I will say that from a qualitative point of view, the oil behavior it's very similar and more or less the same between the two. But not only that, we also found very good correlations between the quantitative data from CFD and dynamic tilt test. For example, in this graph with the red line, we see the measured system pressure. And what we can see is that in correspondence of this point, we had some system pressure ripple, meaning that some air was being sucked until we had a very big system pressure dip. That was the actual issue that we were experiencing in the car. Same if we look at the CFD results, that's the blue line. In this case, we are not measuring pressure, but we are measuring the inflow to our filter. What we notice is that we have a first flow drop and then a second drop bigger in amplitude and magnitude. Of course, there is a shift in time between the CFD and the test results. This is mainly due to the fact that in our transmission, the measurement of the system pressure happens downstream with respect to the point where we are measuring the inflow in the CFD. Another thing that we noticed from the CFD results was this kind of swirling motion. So the oil tended to move along the outer walls of the sampan, leading the peak application of the pump or the inlet of the filter to be exposed to air. So what we did, well, as I said, we were in an advanced stage of our program. We needed to find a quick solution, and we tried to introduce some guiding features, some fins in the sampan, with the idea of forcing the oil to always move towards the center of it, where the inlet of the filter was located. We then performed a CFD simulation to, let's say, to compare the standard sump with a modified one. And what we saw was that during the critical condition, the swirling motion disappeared, and the the inlet of the filter was mainly submerged in oil. We then came up with a first prototype, and we went back on a test bench, and we had a good correlation with what we observed in CFD. Again, here at the top, we have in blue the results from CFD. Sorry, the results with a modified sampan from testing. As we can see, we still had some system pressure ripple, but the big drop in system pressure that we had with normal sampan disappeared. And this is also reflected in the flow measurement through CFD. We can see that, for example, looking at the blue line again, with a modified sampan, the magnitude of the drop in flow rate is halved with respect to the standard sampan. So this is one of the first application of the moving particle simulation to our product, and since then we always use it in our procedure, and we found it really effective. This is all for me, and I will give the word back to Simon, and thank everyone for your attention.
Thank you, Mattia. I'm going to go ahead and pass those moderation rights over to Simon.
Yes, thank you, Mattia, for these very interesting insights. So I will draw a brief conclusion of today's webinar before we go over to the Q&A session. So we have seen that Particleworks provides a robust particle-based workflow, and then also enables CFD simulations in the transmission development. And then, as Mattia pointed out, that this use of CFD in the development process allowed to solve issues that were very difficult to solve before, and that also in a time effective and efficient manner, with some good correlations between simulations and tests, and overall really bringing down the development time in improving the product by also gaining deeper insights into the design. So I think that would be it for today's webinar. I don't know if there are already any questions that came in the meantime.
If it's okay by you, I'm just gonna take those moderation rights back for myself so I can share a short Q&A screen. There you go. All right. Well, first of all, I want to thank you everyone for your attention, and thank you, Mattia and Simon, obviously, for your presentations. As Simon has already stated, we have now reached the end of the session, and I did notice that some of you have sent us some questions through the chat. So we would now like to take a few minutes to answer as many of those as we can. Let me just have a quick look to see which questions I will forward to our speakers. One question I see right here is how close were you able to get the boundary conditions between testing and simulations in terms of accelerations and variable RPMs? Which one of you would like to take on that question?
Can I reply? Well,
yeah,
actually, it's you can apply almost exact boundary condition in terms of acceleration and also input speed. It's just a matter of providing like the exit profile you get from testing or whatever, and you prescribe it to, for example, a certain gear or certain volume. So from that point of view, it's really exact, I would say.
All right, thank you. I believe that answers that question. Another question I see here is how long do one of these simulations simulating 10 seconds real time usually take? Would like to answer that one?
Yes, I think when we did that first project, just going with Particleworks on a workstation using one GPU, I think it was between 2 or 3 days. I don't know what if you want to share any more recent values about your simulations, Mattia, since the software has evolved since then.
I double checked, and for example, for the same simulation, well, of course, then the time will depend on, say, the computational power and also the setting on the simulation itself. So, but for example, for this case, it was 20 hours for 5 seconds of simulation using 2 GPU. With 1 GPU, it was about 30 hours in this case. It was 2.5 million particles, and the size of each particle was 1.3 millimeters. Yeah, in general, I would say it's 5 seconds in one day. But of course, if you have bigger particles, and sometimes we do use, it's not always needed to go with the fine particles. In one day, you can even have 10 seconds or more. So it really depends on the test case. But for a full transmission, for a full gearbox, I would say in general, it's around 5 seconds per day, considering also that the input speed are quite high, and this will have an impact on the time step.
All right, thank you very much for that detailed response. Sorry, I'm just looking at all these questions, so that's why I may come off a little bit distracted, because there's lots of questions coming in right now, which is great. One more question I'm just gonna forward to you guys is how complicated is it to set up such a complete gearbox model? How about that?
I think that really depends on the complexity of the gearbox. So with the one I showed in the introductory part, it can be a matter of a couple of hours. I think, as in many projects, it's always a question of getting or gathering all the boundary conditions correctly, and then obviously also on the complexity of the transmission system.
Makes sense. Thank you very much. As I said, still lots of questions incoming. I have actually forwarded some to you guys, Simon and Mattia. I don't know if there's anything else you'd like to answer right now, or if we should call it a day, because we are approaching 2:45 right now. Can you see the questions I forwarded to you?
Yes, there was one whether it's possible to couple Particleworks with a multi-body software. Yes, this is possible. There is, for example, an existing co-simulation interface with a multi-body software called Ricardo, which can also handle flexible bodies and then also introduce flexible bodies into the Particleworks model. Then one other regarding the post-processing, maybe that should be the last one. Also having a look at the clock, whether it's possible to take cut sections to see the fluid behavior deep inside a large volume of fluid or liquid. Yes, this is of course possible. So since basically the fluid is discretized by our set of particles, we can just, in the visualization, just cut away some particles to get a deeper visualization of the flow also in a larger amount of fluid.
Right, wonderful. Thank you very much for taking the time to answer those additional questions. I would say, having a look at the time, that this concludes our webinar for today, and I would like to once again thank all of you for your attention, and obviously thank you, Mattia, and thank you, Simon, for the time and effort you have invested to make this webinar possible. I want to give you guys a short clap. If there are any more questions from the chat that we have not yet answered, which I see that there are quite a few still, so I'm sorry about that. We won't be able to answer any more questions today, but rest assured that we will get back to you personally on those questions as soon as possible. That being said, all I have left to say, thank you everyone. Thank you for your attention. Thank you for joining us here today. Goodbye and have a great day. Thank you.
Thank you.
Have a good day.
Bye.